turn to the second part, I did this poll in Piazza asking how many people are falling behind. I think about 12 people responded that they are falling behind and are in danger of falling further behind. So I want to give you an opportunity, to basically to start any discussion about any of what we've done so far in class. It could be about asking about the test. It could be something about the probability theory class. Just you can start any discussion on any topic. And the effort is, or the goal is that particularly for the people, let's say, that are falling behind or feeling we went too fast through some issues. Let's try to focus on those kinds of issues. So again, just open up in the chat or speak up, and then we'll get the discussion going. In research, so the question is, in research, how do you motivate your priors? Since it seems a bit subjective to me. It is. And I mean, there has been really a long and vicious debate really about this idea that priors can be subjective. So there are researchers who basically reject the Bayesian framework on the basis of that, because it could be that if you choose another prior than me, and we both use Bayes rule, we get different answers, right? And so a Bayesian would say, and this is exactly how it should be, because you can have a different prior information, right? If I ask you, if we want to come up with, okay, what is the color of somebody's jacket, and that person is around the corner and you are also around the corner, you can see it. But if I'm here, I can't see around the corner. So I would have to say, the color for red is maybe 1 out of 10, and you would see it's a green jacket. So, right. So, so we can have different prior information, and the Bayesian framework, in a sense, allows you to state that. But importantly, then any calculation based on your prior is going to be objective from there on, right? We will use the same calculation Bayes rule, and that is a completely objective calculation. So if you have the important thing is that if you have the same prior, you have to end up with the same conclusions. So that the Bayesian framework guarantees, but we can have different priors. One way of getting priors is what we've done here in this. As you can see, the posterior basically has the same distribution or type of distribution as the prior. So one way of getting priors is just empirically. In a sense, once you can start, let's say, if you really don't know anything, you start with uniform priors, right? And then you just start observing some data, and whatever that posterior is also your new prior for the future, right? So they call it empirical bias. So then the prior is just based on data that you've seen in the past, which basically, if you think about it, is also the way how we get to our subjective priors. So the essence of the Bayesian framework is that the calculation, the reasoning from a prior and a likelihood to, say, conclusions about posterior and evidence, that is objective. Now, and then just to finish the discussion, I see there are also some new questions, which is good, but I'll finish shortly finish it. There is, of course, also a branch in Bayesian statistics that deals with up good priors. because for some variables are only defined on the positive numbers, right? Let's say a mass cannot be negative, right? So then a Gaussian doesn't make sense, but because a Gaussian would go over the whole real line. So what is a good prior for, let's say, a mass or a length, right? And so there is a bit of a theory for that, to how to come up with the equivalent of uniform priors if you really don't know anything, but just the, let's say, the alphabet for that variable. Is that, if that's okay, then I will turn to the next question. And feel free to follow up if it's not okay, right? I was curious. So the next question is, I was curious about vector graphs. How can we get the graph just given the joint probability, or is something that's usually given? I wouldn't know how to factor it. The factorization, or what a vector graph shows, is nothing but a factorization of a function, right? By itself, it doesn't even, it is not, let's say, necessarily attached to probability distributions. If I have a function over many variables and I decide to factorize that function into a set of functions, and each of these, let's say, factors is only a function of a subset of the variables, then I can draw a vector graph, right? And the vector graph will just show the, let's say, the independence structure that I have just assumed by factorizing my function. It's us, the engineers, who set up our models. So we decide on the factorization, but once you have decided a factorization, okay, then you can draw your vector graph. So the question, how can we get the graph just given the joint probability? Well, if there is absolutely no assumption about any factorization, if you just you say, well, I just have a probability over all these variables, and there is no assumption about factorization, then your vector graph is one node, and all the, namely that joint probability, and all the variables sticking out of it, right, by edges. That's your vector graph. But you usually decide on your factorization, and then you can draw, say, a more complex vector graph. So the next question is, so okay, so to finalize that, I wouldn't know how to factor it. No, because you wouldn't know, but maybe you know something about the physics of what's going on, and that will allow you to say, well, this variable is not related to this variable, right? Let's say if I talk about an object, the properties of the object, say the properties, the size and the color, is not related to the location of the object, right? If I move the object, usually the size and the color don't change. So by knowing something about the physics of the problem, you can write down your factorization, and then, but still an assumption that you make, and then you can write your vector graph. So the next question is, how much assumed knowledge do we have to know regarding the distributions? Dirichlet, beta, gamma. Is knowing about the hyperparameters and first, second moments good enough? I think it's useful to know the Gaussian distribution. I think you should be able to write down the Gaussian distribution, and probably the factorial, or let's say the categorical distribution, or maybe the multinomial. Aside from that, gamma distributions, Dirichlet, beta, I will just give these distributions, because and you certainly don't need to know the mean of the beta distribution, or the variance in the, or let's say the second parameter in the gamma distribution. It will be good to know these distributions, in particular to know about these distributions. In particular, I mean, these distributions arise from transformations of variables, right? Let's say the beta distribution is a distribution where it's only on the domain 0 to 1, right? The Gaussian is on the real domain, and the gamma is on the positive domain. So when you start transforming variables, then you need a different distribution, but you certainly don't need to memorize them. It would be good to know that, okay, if we talk about a variable that is only defined on something between 0 and 1, for instance, a probability is a variable, but it can be considered a variable that is only defined on the interval 0 to 1. And you want to set a prior, or you want to set the distribution over that probability, then, the beta is distribution is one distribution, right? So don't have to know them by heart. The discussion, so next question. Okay, this is an answer. An answer from Wouter. The discussion on subjectivity of priors. Yeah, so indeed, there are two camps here, the frequentist and the Bayesian camps. But I think this it used to be between these camps. I don't think that is the case anymore. I think the Bayesian viewpoint is a bit broader and is slowly gained more followers, I think, than the frequentist viewpoint, although it depends also a bit on in which community you are. So let's say in machine learning, the Bayesian viewpoint is really gaining terrain and is very well accepted. Also has an answer. The joint is assumed to be factorized by the designer. That's correct. And so Ismail writes, I'm going to read it out because I know that in the video there will not be, you can't see the chat. So I'll read Ismail's answer. Usually the joint is assumed to be factorized by the designer because the designer up with the model, it's his job to assume a factorized structure. If you're given a joint that is not factorized, then first you need to determine if there is a factorization, right? And like I discussed, that can be on the basis of physical arguments. It might be the case that there's not a factorization or a unique factorization, and these cases are beyond the scope of the course. That being said, the literature is almost always concerned with factorizations that are already present in the joint. That's true because the literature, I mean, factorization is very important because it introduces independencies between variables, and that opens the potential for faster calculations, right? You don't want everything to depend on everything, and the factor graph takes advantage of that opportunity. So that's why a very important factorization that we will get to in the future of this class is in dynamic systems, that you factorized, let's say that we say, well, we consider variables that that sort of represent the current state of the system, and we're going to say that the future of a system only depends on the current state and not on everything in the past, what happened. Everything that in the past that is relevant for the future is represented in the state. And we'll talk about that later. That's a very important factorization in dynamic models. Okay. So feel free to bring up any other point of discussion. It's I mean, it's not the point of discussion here, but I'll bring it up anyway. There is so why is this not a class on deep learning and big neural networks, and how do they relate to each other? So this is really a class on, let's say, information processing, right? It doesn't necessarily pertain just to neural networks. You could apply this to neural networks, but this is sort of like what the proper way of doing information processing, even if you, for whatever model you use, even if it's not a neural network. Now, neural networks are models with a lot of variables, very large set of variables. And the history of neural networks and training neural networks didn't go the Bayesian route. The most important training method is called backpropagation, and this is this is just gradient descent, and you can compare that to say maximum likelihood kind of training. So over the past 10 years, there have been several efforts to bring this Bayesian viewpoint to neural networks, because, I mean, there are some obvious advantages with this Bayesian framework. For instance, we get the evidence. It would be really great if I can get, if I have a neural network and I didn't have to artificially split out some training set and a validation set and a test set, and because those are arbitrary choices, but just train it, and I would get, let's say, the evidence for this model given my data. Turns out that it's very hard to compute, so there's a lot of let's say it's a lot of research over the past few years in how to bring this framework to neural nets, so Bayesian neural networks. And so I think in 5, maybe 10 years, whatever, neural networks are going to be also mostly Bayesian. Maybe not, because it's a projection, right? Maybe not, but I think it will be. Just every week or every month, there's some new paper coming out in this field. For instance, this morning I saw there's a new paper out that shows that that neural networks. It's something that we'll get to later. It has to do with factorization in the posterior, namely a mean field assumption in the posterior is a very good thing to do for a neural network. But you can forget about that comment. The idea is that there is let's say, this Bayesian framework of how to do information processing, and the neural network literature are coming together currently let's say, in the machine learning literature. Is a Bayesian framework a black box type of model? Is it possible to perform some form of sensitivity test for the inputs on the outputs? I think I'm not sure exactly what you mean by that, but it is, and maybe some of the others may want to join in and answer that. But what the Bayesian framework you particularly give is if you can frame it as an inference task in your model, then it's, let's say, purely Bayesian. So I don't want to, let's say, skip over the question, is Bayesian framework a black box type of model? Not necessarily. Is it possible to perform some form of sensitivity test for the inputs on the outputs? Well, you can, of course. I mean, I see a sensitivity test as can you differentiate through your network? Can you differentiate your output to your inputs? You can, of course. You can differentiate. I mean, in the Bayesian framework, your model is a probability distribution. Probability distribution function of variables, and you can do your you can differentiate through functions. So technically, yes, there's nothing that stops you from doing these sensitivity tests. So how about reinforcement learning? Do you think there should be a link between Bayesian framework and reinforcement learning? So reinforcement learning is the idea of learning how to take actions. What we've done so far is, well, the machine learning that we've done so far is we've said, okay, I have a model, and this model has parameters, and now I have a data set. And I need to sort of absorb this data set in my model, in my parameters. And that we do with Bayes rule. Reinforcement learning talks about agents. So these agents can take actions in the world and make decisions. Like in a sense, we are reinforcement learning agents, right? If I change the position of my head, I get different data. I get different sensory inputs. So reinforcement learning, we can take actions, and that will change our data. And that makes things a whole lot more complex, because if so what we usually do in reinforcement learning is to have a sort of a reward function for that sort of ranks future behavior, and we want to take the actions that sort of maximizes that future reward. So there's a cost function, and then you try to maximize your reward or minimize your expected costs, and then you want to take the action that will do that. In the Bayesian framework, you can also do this completely Bayesian. There's nothing you can do it not in a Bayesian way. You can also do it in a Bayesian way. What we will do later in the class, we will do a fully Bayesian approach to reinforcement learning. Although we call it something, we call it a bit different. We call it active inference, but it is a fully, let's say, Bayesian approach to learning how to take actions. So there's a question on mathematical derivations and notations, and they're unfamiliar. Like the Gaussian notation, n of x, and then given AE. That notation always means this is a Gaussian distribution over x, and the mean value. So the Gaussian distribution has two parameters, a mean value and a variance or covariance matrix. And the mean is in this case A, and the variance or the variance matrix is E here. The notation is always Gaussian of a distribution, then I have the arguments, and then I have the bar, and then I have the parameters of that distribution, and they're in fixed order. If I would exchange A and E here, then I basically am saying then, oh, E is my mean and A is my covariance matrix. Yeah, the second one, the gradient of log of the determinant of A, the gradient, so the derivative with respect to A is A transpose to the power minus 1. This is just the matrix equivalent of saying that the derivative of log x is 1 over x. This is just matrix calculus. So in Bishop's book, I think in one of the appendices, there is a short section on matrix calculus. And so the only thing I can say there is, yeah, look at Bishop's book. And otherwise, at the end of this class, by the way, here, these are all the formulas really that we use of matrix calculus, and they're in Appendix C in Bishop. And Bishop also derives these formulas. And so what I do in this class, I list them here, and then I just use them. And if you want to know how to derive this, you should read the book, or you should read the appendix, really. And these things you don't have to remember. I think with all these things, the same thing is true for the gamma distribution and the beta distribution. They're hard to remember unless you work with them. If you work with them, you'll remember them anyway. And if you don't work with them, then you'll forget them. So I don't expect you to remember these formulas. If you are in some project and you work with them, you'll remember them anyway. So what I would do in an exam is I would just list this. If I think, okay, we're going to need some of these formulas, I'm just going to list them on top of the exam. Or I'm going to say, and here's the gamma distribution, here's the beta, and here's the Dirichlet. And I'll let you pick the one that you want. All right. So for these formulas, I don't expect you to, to remember them. And I don't think, I mean, the question is, it seems to me that this is something that we have to know prior to this course. Is it the case, or are we supposed to learn them in the course? Let's say for the matrix calculus, I only want to use this, so Appendix C. And so expect you to, I mean, maybe to read Appendix C once. So you have a kind of a feeling for how they are derived, and then just look at the table when you need to use them. So Magnus mentions that there are indeed many ways to work with reinforcement learning tasks using Bayesian machine learning. It's a whole subfield on its own. Indeed, we're going to look at the idea of agents too at the end of the course. That's right. So reinforcement learning and Bayesian machine learning are not the same, but you can apply the Bayesian framework to reinforcement learning. Right. This Bayesian framework is a way of doing information processing. The way we look at it here is you describe states of knowledge by probability distributions, right? Your beliefs about something you describe by probability distributions. In a sense, information processing is updating states of knowledge when new information becomes available. So that's what probability theory does. So for me, information processing is just updating probability distributions as new information comes along. Information usually comes along in the form of observations, and then we use Bayes' rule. But I mean, there are other ways how new observations can appear, right? Could be that, or let's say how new information can appear, right? It could be that, so let's say there could be some constraints in the physical world that you cannot walk through a wall, right? These are just, and you just happen to see that wall. So there's a new constraint rather than a new, just some data observation. But for me, information processing is applied probability theory. Applied to machine learning, it turns out that probability theory prescribes Bayes' rule. And so Bayes' rule assumes that you have a model, and then it's you can apply that, of course, to all these different branches of machine learning: reinforcement learning, classification, regression, and we're going to do a few of them, right? And that model may be a neural net. It doesn't have to be a neural net. Okay. So there's Wouter has a extension or sort of on the Bayesian framework. So what we've done so far, indeed, is we use basically models with a fixed number of parameters, right? And then we, when we make observations, when we say, oh, now I'm going to do machine learning, basically that means I'm going to sort of try to absorb the information that's in the data in my fixed set of parameters. So I'm going to change the parameter values or update my state of knowledge about parameter values. There are models, other types of models that are memory based and that don't have a fixed number of parameters, but you can say, well, if the data set keeps growing, is it a good idea to just keep my parameter set fixed, or should my parameter set also start growing? Well, if you have a growing parameter set, we call them non-parametric models, and we're not going to do it in this class, but it's still, you can still apply this Bayesian framework, right? Yeah, so in short, I mean, just to summarize some of the answers here, this class is about how to do information processing in general, and then we decided I wanted to make an argument for the proper way to do that is through probability theory. And in a sense, we define information processing as updating probability distributions when new information becomes available. And you can apply that to, let's say, when data becomes available and you have a model, you can apply, and then we call it machine learning or Bayesian machine learning. And we have started with the two simplest models that you can think of, the Gaussian distribution and let's say the categorical distribution. Those are the two simplest models, right? One is for discrete data, one for continuous data. You can't come up with simpler models than that. So now after this, we're going to start sort of ramping up our model classes. The framework is all done. The probability theory is all done. The Bayesian machine learning framework is all done. We just had our first two classes on how to do this with the Gaussian and the multinomial. And now we're going to start building models. And yeah, as it turns out, if you want to keep things, let's say, analytically tractable, and in this class mostly we do, then the models are sort of then this Gaussian and the multinomial are sort of blocks for our models, right? So we'll see, for instance, in classification that this Gaussian updating comes back, and also in classification, the one-hot coding mechanism comes back. So we will start doing some more interesting applications than what we have done now, but what we have seen so far will come back, right? So we're going to, it's not just for abstract, let's say, use. It's we're going to actually use some of it in the future. But I don't think there's going to be conceptual difficulties after this class, perhaps with the exception of the class on latent variables. That's an idea. And then we introduce also an approximate Bayesian thing. So that's a new class. Aside from that, I don't think there's going to be really conceptual new things in this class. It's just building models now and applying this recipe of coming up with a prior, a likelihood, computing the posterior, and that's going to be it. That's sort of the power of the approach, right? I'm not sure if we've answered all the questions so far. If I've missed a question, maybe you can copy paste it. So. Okay, so I don't see anything in the chat. Perhaps somebody wants to say something, particularly if it's in relation to the class, it would be good. But if you want to say something else, that's also fine. Okay. Um, yeah. So then, so next time we're going to have a probabilistic programming class again. So this will be Friday. Um, I see there's just one more question. What general and metric in Bayesian machine learning framework as a stopping criteria for your model or the posterior? Um, well, technically, if you can do perfect Bayesian inference, so if you can do if you can actually analytically compute the posterior evidence, then you don't need stopping criterion. You just do your Bayesian inference and you're done. Right, so it's a one-shot thing. The proper answer to, let's say, once you have a prior and a likelihood, the proper answer for Bayesian machine learning is compute your evidence and compute your posterior. The evidence will tell you if this is a good model, and the posterior will basically have fused what you stated you knew about your parameters and what the data tells you about your parameters. So there is no stopping criterion. Now, later on in the latent variable class, we're going to see that, yeah, for some models, we can't actually execute Bayes rule analytics. Then we're going to do a trick. We're going to rephrase this as an optimization problem. And so now we have a function that we need to minimize. And then, of course, the question is, when do I stop minimizing, right? The nice thing about the Bayesian framework is that because I have this prior, that there is sort of a built-in trade-off between getting more accurate and at the same time not increasing. There's a penalty for increasing the complexity of my network. I wouldn't get this if I didn't have a Bayesian framework. I wouldn't get this if I do maximum likelihood. If with maximum likelihood, you can actually just keep tuning and tuning and tuning until you tune to all the observations exactly, and you would sort of overshoot because you also tune now to all the noise that you have observed. So if you don't do a Bayesian framework, but you do, let's say, gradient descent on some sum of squared errors, then you need an additional stopping criterion. You need to say, okay, I have this validation set. I'm going to stop if my sum of squared errors starts to rise on my validation set. We don't have that in the Bayesian framework. You cannot overfit. But so this is something that we will treat once we do approximate Bayesian inference, right? So I don't want to talk too much about it because it will come back in the latent variable class. Up to what we have done now, there is no such thing as a stopping criterion because you just execute Bayes rule. In the future, we'll start minimizing a cost function to do approximate Bayesian inference, and then we stop when we don't get lower, but we never have to have with our, let's say, with our function, we just try to minimize it and we want to get as low as possible. But there is no risk of really overfitting. And one way of seeing that is that once you have set your prior and you have set your likelihood, you have implicitly already set your evidence. Right? The evidence is just the integral. So you are. It's just now in our sort of a rephrasing the information, the same information in two different factors, evidence and posterior, but you're not changing the complexity of your network by doing Bayesian inference. So I hope that sort of answers it. Otherwise, I hope it will come back later when we do variational Bayesian inference, where we start minimizing a cost function. So then I was saying, so Friday, we're going to do probabilistic programming. So that will be a class that after that, we're going to start building, let's say, more interesting models. So far, it was maybe interesting from a theoretical or framework viewpoint, if you like this kind of stuff. But the idea is that as we go on now, that we actually start looking at some applications of this framework. And that will start, basically next Wednesday. And so let me know also if, because I've seen that some people have fallen behind, if this doesn't get better, you start falling further behind. So let me know. You can send in Piazza anonymous, or you can send private emails to me if you want. I prefer if you do it through Piazza than through email, because emails may get lost. I get lots of emails. So in Piazza, I know it's from the class. So I prefer that. Just send me a private email, and then hopefully then I can sort of gauge when we want to do again a meeting like this, where we go over the whole thing again, or at least open it up for talking. Yeah. Okay, so if there's no more comments or questions, then I'm going to finish the class. I'm going to wait 5 more seconds for anybody to speak up or write. Okay. Thanks. It was an interesting discussion. I'm really happy with the way also that you collaborate on getting answers to questions in Piazza. They're good questions, and the large majority of answers by the students are right on the mark. So I'm really happy with that. So keep going with that, and then we'll see you upcoming Friday. Okay, bye-bye.